Let's look at an example of a one-way analysis of variance. We have data from a bunch of babies. We've measured their birth weight, our nice continuous variable. We can summarize them with the mean. And we look at where those babies are distributed across this categorical variable. And our research question, our null hypothesis is, are those four groups equal or not? So our outcome is going to be birth weight. The factor or the predictor, the X, the independent variable is which hospital they are, right? And we're going to say, does birth weight depend on what hospital you're in? That's why it's called the dependent variable. You can point and click your way in Stata through this one-way ANOVA. Now think for a second. The first thing we always do is look at the data. Look at the data. What do you think this is going to be? Do you think this is statistically significant or not? Take a guess. Write down what you think the p-value will be. If you had to describe right now what these data look like, what would you say? Well, hospital A looks lower than hospitals B, C, and D. And I might even add, those look about the same. So hospital A looks lower than B, C, and D, which don't look to differ between. Right? Now, can you write that up to the New England Journal of Babies? No. You have to put a p-value on it. This is the game. These are the rules. So we'll set your alpha level. Let's say we'll set it at 0.05. And we'll say, let's summarize this with an F statistic and say, what's the probability of getting that F statistic by just throwing a bunch of babies at the wall randomly? Because this doesn't look random, does it? It looks like there's some sort of pattern. And we'll say, what's the chance of getting this pattern if things were random? That's our p-value. That's what this is. Statistics is backward. Here is Stata output for this test. In Stata, you can say one way. That tells Stata I'm about to run an ANOVA. We've seen that in Stata, you usually put the outcome or the dependent variable first. Take ANOVA and then see how it is. Sorry, take ANOVA. That was dumb. Take birth weight and see how it's sort of distributed across those hospitals. We put in this option here, tabulate, because it makes this nice little tabulate means put it into a table. Now, what we're going to see is how F works is it's a ratio of what's going on between the groups relative to what's going on within the groups. The details here aren't important. I don't care about this. But you take these numbers and you divide by roughly the number of groups you have and roughly the number of babies you have, and you get these numbers, the mean square. When you look at that mean square, you put them on top of each other, and that turns into F. What's the probability of getting that F if the null is true? It's very, very small. P is less than 0.0001. So we reject the null hypothesis. And that difference that we see that, I have a very dangerous word on this slide here. You guys see it? I have cause down there. Ugh. Be careful about that. The difference due to hospital, that's even close to. Okay, the difference between hospitals is a little bit different relative to within. And here we see the actual means and the standard deviations. So there is a difference. But where? So F tells us that between relative to within, there's a signal there. P is less than 0.05. Reject the null and say the means are not equal. But where is the difference? Now, think about this for a second. I have four groups. And I know that all four are not equal to each other. Somewhere in there must be a difference or differences or something. How could I find what those differences are? Comparing the mean between each group, well, that just sounds like running a bunch of t-tests. So we find this thing which is called the post hoc test, after the fact. And Fisher, who helped come up with this idea of ANOVA, and that's why it's called an F test, is said what you should do is run the overall test to see if there is a difference, and then run all possible t-tests. And this has an approach called Fisher's LSD. And if you want to go through it in Stata, here's the point and click, and then here's the code. PW, pairwise, right? You run all possible t-tests. Well, how many are there? There's A against B, A against C, A against D, blah, 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 right? All those possible pairwise ones. And Stata will do that for us. So this is the table. This is what I just said. A against B, A against C, and so on. So here are the 6 t-tests that are possible when you have 4 groups. And what you see here is that look at B relative to A. Well, B, the birth weight is higher than A. And it is statistically significant. Remember what these data look like. We had A, and then B, and then C, and then D. There's our box plots. The worst boxes you'll ever see. A, B, C, and D. And here's birth weight. A, remember we said A looks lower than B, C, and D, which don't seem to differ from each other. Well, now we can even say, on the average, babies born in hospital A are significantly lower than babies born in hospital B and C and D, period? No, comma. On the average, babies born in hospital A are significantly lower than B, C, and D, comma, and then look here, which do not differ from each other. A one-sentence summary of 6 t-tests. On the average, babies born in hospital A are significantly smaller than those born in B, C, and D, which do not differ from each other. That's it. That's your one sentence. Now, here's a bit of a mind bender. Pause and take 3 deep breaths. Now that you've paused and taken 3 deep breaths, check this out. An ANOVA is a type of regression. If I said, hey, I want to compare the mean birth weight between 4 hospitals, you might think, okay, mean birth weight, continuous outcome, 4 hospitals, categorical predictor. I'll make those into dummy variables and see if they're different. So if you do this in Stata, remember when we put multi-level categorical variables into a regression, we said first we have to turn them into binary variables by making dummy variables or those reference variables. Let's regress birth weight. How does birth weight depend on which hospital you're born in? See that I dot? That makes the dummy variables. And we see, check this out, there is a difference somewhere. Modeling or using hospital to predict someone's birth weight is better than not using it at all. There is a difference somewhere. Where is the difference? Well, it looks like, remember how we did this? We get a slope here for B. And that slope is relative to the reference, which is the one here that's missing, which is clearly hospital A. On the average, babies born in hospital A are significantly lower than those born in hospital B. These results are the exact same as the results from the ANOVA because the ANOVA is a regression. Play with this, practice this. This is a really important thing to learn. When we're talking about our continuous outcome variable that we're trying to predict the mean for, we can really put everything we've done under this umbrella of regression. If we have a predictor or predictors that are continuous, people will call this a linear regression. Remember, X, Y, bunch of dots, draw a line. Okay, we call that a simple linear regression. Simple because there was one predictor. What if we added another variable and we had 2 continuous predictors? We saw that we had coming out into 3-dimensional space. You see how my hands are getting bigger? That's mean I'm 3-dimensional space. The babies are floating around us. Our model is now some sort of plane instead of just some sort of flat line. We call that a multiple linear regression. But it's the same as this, it's just that we're in 3-dimensional space. Now think of this for a second. Remember we said, let's say, does maternal age affect birth weight? Does maternal age affect birth weight? Well, maybe look at the scatter plot here. Maybe this is age. Maybe that's maternal age. I have younger women, I have older women, and I draw a line. But say for a second, imagine when you collected the data, instead of collecting age as continuous, you would collect it as categorical. Are you a teen mom? Are you a really old mom? Or somewhere in the middle? All right. So if I could take that age, watch this. I'm going to take all these dots, and I'm going to take all these dots. There's my teen moms. I'll take all these dots. There's my, we'll call it old moms. And then I'll take all these dots, and we'll call it, I don't know, middle moms or something like that. If I look at those and I recategorize them into 3 groups, what do my data look like? Oh, this is very interesting. If I take this as categorical, now what does that look like? There's age, which is categorical. Well, now that's called an ANOVA. And so if you have categorical predictors, we just call it an ANOVA. Now, you see all sorts of other terminology, and it can get overwhelming. Sometimes when you have a mix of categorical and continuous, people will throw this in and call it an ANCOVA. But for me, it's all just a type of regression. And imagine this. When I took that age and I recategorized those women, what if I just said they're young or old? I have a bunch of young women and a bunch of old women. And I would say, what's the mean birth weight comparing young women and old women? What does this look like? Well, I almost swore. well, heck, it's a t-test comparing the mean between 2 groups. But all of this is a type of regression. This next slide, you might hate it, but this next slide is an umbrella of everything that we've done. Let's take a minute and look at this. Can we conceptualize everything we've done in terms of a regression, where we're trying to predict the mean of some outcome? And remember, when we think about things in the population level, we realize that our predictions are never perfect. And there's always going to be some sort of error or some sort of leftover. That's why we see that Greek letter there, epsilon, for the error. But if you look at this slide, let's say I have one predictor variable and it's continuous. Well, basically what we're doing there is a correlation. If I have one predictor variable and it's binary, basically, not basic, sorry, I say basically, I should be saying basically, I say this. It's a t-test. If I have a lot of predictors and they're categorical, I almost said basically again, it's an ANOVA. Right there. There's our boxes and it's an ANOVA. Right? So all these things are t-tests. Now, teaser. What if your outcome is not continuous? Well, now we need to go into some other tools, and we'll do this soon, logistic regression. Remember we talked in the thing, what is the best model? When we have a whole bunch of predictor variables. If you have more predictors than you can deal with, that's a you problem. If you have more predictors than you can deal with, what do I do? Well, we said you can just, fit a bunch of different models and compare them. Either let the computer do it for you, or you look and say, what's the best model? Or we might do an advanced stuff. We're not going to cover it in this class, but you will, is we can use the data themselves to see if there are clusters or if there are some underlying components that are driving what we see. This is awesome. This is everything that we've done. Even the weird stuff that we've done. What if your outcome is not linear? Well, I don't know. Transform it. Maybe try a log. And you'll see if you go on in other courses, maybe there's ways to fit things other than lines. And then we also teased a little bit when we did regression diagnostics. We said, let's take a little time and think about this error term, these residuals. Does it meet our assumptions? Is it normal? Are there outliers? And then we see some more advanced stuff too. If the residuals are not independent, we can do some more advanced things. This is an awesome slide. When you first see it, you hate it. But then when you see it again, you hate it. But when you understand it, you realize this is a great overview of everything that we've done and everything that we're going to do, except what we do next week. We will look at one more ANOVA example in a minute.